All right, so in class today, we talked about specific energy and fuels and rating fuels based on how much energy they have per kilogram. And now I want to just show you a few examples of how we use that in practice. And here we're going to talk about different fuels that we use to heat houses. Now in Ghana, we don't do that, but in most of the Northern Hemisphere, we use furnaces to heat air in houses. And these furnaces look a lot like that, where you have rails of natural gas being burned, creating this flame, which then heats air that is then pumped through the entire house. Okay, so we're going to use that as an example to calculate heating power. So the objective of this little video is to practice using the values of a specific energy of different fuels to calculate heating power and fuel consumption. This is a common type of problem that you can face when we're looking at heating water or heating air or heating substances using fuels. All right, so in this furnace, let's just start off by looking at the energy transformations. You start off with chemical potential energy, and that chemical potential energy is then converted into thermal. It's a pretty simple one-step conversion. However, thermal energy that's produced by the flame is going to be dissipated in the form of radiation. Okay, you're seeing light. So not all of that heat energy or thermal energy is going into heating the air. Some of it is going into light, and then some of it is going to be not going into the air. It's going to be conducted away. So that's conduction, radiation conduction, conducted into the metal or materials surrounding that flame. And the last is convection, and that's how heat is going to flow. So once the air is hot, it's going to move by convection. So not all of that thermal energy that's produced by chemical potential energy is going to go directly into the air. Some of it by conduction and convection is going to be going into the air. And so none of these furnaces are 100% efficient. When we're burning that fuel, we can calculate theoretically how much heat is coming out, but only a fraction or a percentage of it is going into the air to heat the house. So we're going to talk about that in this little practice problems. So the first practice problem that I set up is a natural gas heating furnace burns 10 grams of methane per second. Assuming only 65% of the heat released from combustion is used to heat air in the house, as I just talked about right now, calculate the effective heating power of natural gas in the furnace. Okay, so what we need to remember is, I'm just going to change the color, power is measured in watts, which is joules per second. So this question is asking to find how many joules of energy is released by 10 grams per second. Okay, so already I know I'm burning 10 grams of methane per second, and 65% of that is going into the air. How do I combine all these variables to figure out the power? Okay, so in the previous video, I showed you what the specific energy of methane is. So we need to go back up to that table. Here's the table. So methane is natural gas. Oh, why is this doing that to me? Methane is natural gas, and I'm going to use the lower end of the spectrum. So natural gas has a specific energy of 46.5 megajoules per kilogram. So I'm going to write that down over here. So the specific energy of methane, which is natural gas, is, 46.5 megajoules per kilogram. Okay, I need that value. Now that I have that value, I can look at 10 grams. What is 10 grams of that? And that's being burned every second. So that would tell me the theoretical power. All right, so first I'm going to look at if 100% of the energy, if 100% of energy is released, well, then I would take the specific energy, which is 46.5 megajoules per kilogram, and I would multiply that by how many kilograms is there in 10 grams. So in every second, I will multiply this by 0.010 kilograms per second. My kilograms are going to cancel out. And if I multiply those two values together, I'm going to be left with Oops. Why is it doing this? 0.465 megajoules per second. Wow. Okay, so then that's a lot. If I'm burning 10 grams of methane per second, I'm producing 0.465 megajoules per second. Except that's not exactly what's happening. Only 65% of that is actually going, only 65% of that is actually going into the house. So then I would have to find, for 65%, I will take 0.465 megajoules per second multiplied by 0.65, and that will give me the actual power that is going into the house. So here, I'm just going to pull up my calculator. So 0.465 times 0.65 gives me 0.30 megawatts, okay, because a megajoule per second. So 0.30 megawatts, or 300 kilowatts. Okay, another way of saying that is 300 kilowatts of heat energy. So that would be something that if I'm heating like a school or a big volume of air, then 300 kilowatts, 300,000 joules per second of heat energy is going into air. Well, then you're trying to heat a giant building. Okay, so that would be a furnace for a very giant building. So that furnace is burning 10 grams of methane per second. So it's really consuming a lot of methane to burn that. Okay, so just to walk through this again, the important things you need to know is the rate of fuel consumption, grams per second. Okay, that'll allow me to convert my specific energy by multiplying those two together to get power. And power, remember, is joules per second. So megajoules per kilogram times kilograms per second, the kilograms canceled out, leaving megajoules per second, which is watts, megawatts, megajoules per second, or megawatts. So, and then using the percentage, 0.65 is 65%. This would be 100%. So 0.65 times that gives me the actual energy or power being put into the air. So that's how I use that percentage. Okay, so you can walk through that a few times to be able to use it. Now in the second question, we're going to go a little bit backwards. Here I have calculate the rate of methane fuel consumption. Okay, well the rate means in grams per second or kilograms per second is equal to my rate. Okay, so that's what they're looking for. In a furnace that is 70% efficient and produces a heating power of 10 kilowatts. Okay, so that's going to be less than what we did over there. So let's try to figure that out. So the final product, the power that it produces, is 10 kilojoules per second, or 10,000 joules per second. Okay, and what I need to know about the specific energy of methane is, again, 46.5 megajoules per kilogram. All right, or if I want to convert it into kilojoules, 46,500 kilojoules per kilogram. Okay, so I have to try to find some common units here to figure things out. All right, so that's how much energy is in a kilogram of that methane. And what we're trying to figure out is how many kilograms per second of methane is being used to produce 10 kilowatts, okay? And that 10 kilowatts is produced after 70%, all right? So we'll have to go backwards. So the final power is equal to 10 kilowatts, okay? And then that's after 70%. So let's find out what the actual power being produced by that furnace is if energy wasn't lost. So 10 kilowatts divided by 0.7 will give me the actual power, theoretical of furnace. So 10 divided by 0.7 means that I am actually burning to create 14.3 kilowatts of heat. So 14.3 kilowatts is 14.3 kilojoules per second. So now I need to figure out how many kilograms per second. Okay, so let's write down these units. I got 14.3 kilojoules per second, and I have 46,500 kilojoules per kilogram of methane. So how am I going to do this? Well, I need to get kilograms per second. My final answer needs to be kilograms per second. So how do I combine this and this? Well, kilograms needs to be on the top. So if I take this number and I divide it by that number, I should cancel the units to get my answer. So 14.3 kilojoules per second divided by 46,500 kilojoules per kilogram. The kilojoules cancel out. The kilogram is going to go to the top. Seconds are going to go to the bottom. And that is going to give me the units of kilograms per second. So if I do my calculations divided by, that gives me 3 times 10 to the minus 4 kilograms per second. So that furnace has to burn 0.3 grams or 300 milligrams per second. So that furnace is burning 300 milligrams per second of methane to create 10 kilowatts of heating power. And that would be a very small heater, such as your stove. Okay, your stove that you're using for cooking is probably burning around 300 milligrams of methane per second if you have it on full blast. Okay, and that's how you can calculate how long a tank of gas is going to last. The tank is probably about 25 kilograms. So then you can calculate how long you can use that tank of gas to cook on your stove. Okay, so going back just to review this problem we have to go backwards. 10 kilowatts is the actual power that came out. If I divide 10 kilowatts by 70%, that tells me the actual heat being produced by burning the methane. Okay, and that gave us around 14 kilowatts. Once I had the heat being produced by methane, I could then use the specific energy and create a ratio like this to find out how many kilograms per second. And all that ratio was created by trying to cancel units out so that the units match what I'm looking for. Okay, so that's the key to these problems. So you'll have lots of chances to practice this in the SOCOS Test Yourself questions that I assigned for homework.